Standard enthalpies of formation. The standard enthalpy of formation of something, denoted by delta HF superscript 0, is the enthalpy change when 1 mole of a substance at standard pressure, meaning 1 atmosphere and 298 Kelvin, 25 degrees C, forms from its constituent elements in their standard state. The something can be a formula unit, molecular or ionic, an atom, or an ion. An element is in its standard state if it is in its most stable form at standard pressure and 298 Kelvin. So if it's at 298 Kelvin in 1 atmosphere, meaning room temperature conditions, the elemental state, that's what makes up the species that is forming some formation of some product. Example, let's look at silver chloride. What is the elemental state of silver at room temperature? It's an element. So if I take that silver solid, and let's say we take chlorine, what is the elemental state of chlorine at room temperature? Chlorine gas, Cl2. So if I take those and add them up and form silver chloride, it'll tell me the reaction for that formation, and there's a delta H associated with that, a delta HF. So I have silver solid plus chlorine gas gives me silver chloride solid. There's a delta HF associated with that, a heat of formation that we can use to calculate heats of reaction. Now the one key here though is, by definition, it's the formation of 1 mole of the substance. So we're saying that this has to have a coefficient of 1, so then we have to balance this equation for that 1 to be a coefficient, which means that we could have some fractions in our reactions for our delta HF reactions. Note that the standard enthalpy of formation for a pure element in its standard state, and also the hydrogen ion, are 0. This means elements in their standard state have a delta HF of 0. So typically on your periodic table, you know that all your elements and metals tend to be solid at room temperature. They have a delta HF of 0. Your diatomic gases tend to have a delta HF of 0, and your hydrogen ion. This is set as our standard, okay, as our comparison, as this is a relative scale. So we're saying all elemental states of elements in their natural standard conditions, 298 Kelvin, and that's 25 degrees C in 1 atmosphere, those are delta HFs of 0. So when you see a problem, you may not be given a delta HF because it's its elemental form, which is a delta HF of 0. So you're going to have to remember that as you're doing your calculations. Another way to determine the heat of reaction is the law of summations of heats of formations, which states that the enthalpy of a reaction is equal to the total formation energy of the products minus that of the reactants. Basically, we can't do Hess's law for everything. We don't have reactions for every reaction possible. So then we also can look at it on a molecular scale as a molecule of the substances. So we can do it on the delta HF, the heats of formations of the different substances, and figure out the delta H of a reaction from that method. So basically what we're saying here is the delta H of reaction is equal to the summation of your number of moles of each of your delta HFs of your products minus the summation of the number of moles times each of your delta HF of your reactants. This is products minus reactants. And you must account for the number of moles of each of the species. So the summation symbol means the sum of, and the n is the coefficients of the substances in the chemical equations. So let's do a generic one before we can show you what we're talking about with this formula. So here's how you set up a calculation using the laws of summation for a generic reaction. I have some small a, meaning number of A moles of some A substance, some B moles of B, some C moles of C, and D moles of D, where all the small letters are moles. These are your moles, and the large letters are your substances. So, delta H is equal to your summations of your delta HFs of your products minus your delta H of your reactants. So we will set this up. Okay, the summations of your products, which is on your right side. We're saying small c, moles of C, time your delta HF of C. So your moles cancel, and I'm left with kilojoules, which is a heat term. And then I do the same thing with D. I have D moles, meaning the small number, the coefficient in front of D, time its delta HF of D. Then I'm going to subtract that from the summation of my reactants. Once again, have my moles, small moles of A, time my delta HF of A, moles cancel, kilojoules, and account for my delta HF of my B, and accounting for the moles as well. So let's see if we can do this in a problem. What is the standard reaction enthalpy, the delta H of reaction, for the following reaction? I got 4 ammonias, 5 oxygens, 4 NOs, and 6 water gases. It's important as I look in tables that I know the states, because my water could be a liquid, could be a gas. I've got to make sure I'm pulling the right one from the equation. Now, for the most part, you'll be given that on the test or in your homework. So there's no reactions for me to compare using Hess's law. So one thing I can do is go to tables and look at my delta HFs. If I look at it, I find that ammonia has a negative 45.9 kilojoules per mole for gases. NO gases is 90.3, and H2O gas is a negative 241.8 kilojoules per mole. But what about oxygen? I looked in the table and I can't find it there. Why wouldn't there be any number for oxygen? It goes back to what we said. Elemental states at room temperature, 1 atmosphere, their delta HFs are 0. So that may not be given to you in a problem. You just got to realize that it's 0, okay? Because it's not there because it's its elemental state. That's how the element is at room temperature in 1 atmosphere. Next, we use the law of summations and plug the values into the calculation, into the summation of products minus the summation of reactants of our delta HF, so formation. So using the summation law, we now know that we have our products. So I have my 4 moles of my NO time its delta HF. My moles of NO cancel, leaving me in kilojoules. Then I have my 6 moles of my water and my delta HF of water. Moles of water cancels. So now I have kilojoules of my products adding up. Then I have 4 moles of my NH3 and my delta HF of NH3. And we know that 0 for my delta HF times my 5, which is still 0. Clean that up a little bit. So I have all my units canceling out. So that leaves me 4 times 90.3, which gets me 361.2 kilojoules. My 6 times my negative 241.8, which is a negative 14.50 of 1,450.8 kilojoules. I'm summing those, so I'm going to add that. So I'm adding a positive and negative number. Then I have my 4 times negative 45.9, which is a negative 183, and then my 0. Now remember, this is my products minus my reactants. Okay? So I'm going to take the sum of the products and the sum of my reactants and subtract them. So if I take 361.2 and a negative 1450, I get a negative 1089.6. If I take a negative 183.6 and 0, I get a negative 183.6, but I'm changing the sign, which makes this a positive. Add the numbers up, I get a negative 906 kilojoules. The negative sign is an indication that this is an exothermic reaction. I got 906 kilojoules of energy that's being released. So the final answer, delta H reaction, is a negative 906 kilojoules, or in other words, 906 kilojoules of energy being released. Now, the whole problem with this is not the plugging and chugging, it's more of the arithmetic and signs. Make sure you're careful in following your signs and you're plugging the numbers in the right location as you do your calculation. Homework 56.